If you're into sound, whether it's recording, installation, or serious listening, you've probably heard of comb filtering, standing waves, and room modes. They are a result of a room's dimensions and how sound waves are reflected within the room. This demonstration, without getting overly technical or using a lot of math, will show how these reflections can affect what you hear, and using acoustic treatment to reduce reflections can improve a listening or performance environment. Sound waves are a series of high and low air pressure zones which can be represented in a drawing. This area represents a high pressure or compressed air zone, and low pressure or stretched air is shown here. The waveform indicates the rise and fall in air pressure. As sound waves reflect off the walls, floor, or ceiling, certain frequencies can boost or cancel themselves. The length, width, and height of a room determine these frequencies. And to make matters even a little more complicated, this boosting or canceling also changes with the listening position. And now the demonstration. Here we have a speaker that will play a tone. It's just like this speaker. A microphone connected to a VU meter, and a wall to reflect sound. This demo uses a mid-range tone with a wavelength related to the size of these waveform drawings. The microphone and speaker move together with a waveform drawing that represents the direct sound from the speaker. The lower wave drawing represents the sound reflecting off the wall. When the peaks of pressure in the direct and reflected sound waves line up or are in phase, you will see a boost in the level at the microphone. Consequently, when the pressure peaks of the direct sound line up with the dips of the reflected sound pressure, you will see a reduction in level. This is an out-of-phase condition. I'll start the tone and move the speaker. We've seen a variation in level from +3 to -20, well over a 20 dB swing. Peaks and dips in response can also be found by moving a microphone around a room. These peaks and dips in frequency response can be altered or smoothed out by changing the size of the room, not usually an option, moving the speakers, moving the listening position, or installing absorption in the paths of reflection. I'll place a fabric-covered fiberglass acoustic panel against the wall. With absorption in the path of the reflection, we've seen much less variation in level, only a 9 dB swing instead of the over 20 dB swing caused by the hard reflection. Note that treating an area with acoustic improvements first will yield much better results than attempting to correct sound problems only with electronics, and there are some problems that acoustic changes can fix that electronics cannot. I hope this demo has shown how sound reflections can create comb filtering, standing waves, and room modes, which affect a listening or performance environment, and acoustic treatment can be used to control reflections that cause peaks and valleys in frequency response. For more information or to purchase acoustic materials, please contact Acoustics First.